Okay, so we need a solution concept for stochastic games because, as I said, in stochastic games, we're back in a multi-objective optimization setting. So there is no longer a kind of uniquely determined notion of maximality like there is for the one-player setting, which is Markov precision processes. So the main solution concept we use for stochastic games is called a Markov perfect equilibrium. So by this point, you can start to see some patterns in the terminology. The word perfect in a solution concept means something like optimal in every state. So in this case, the perfect in Markov perfect equilibrium means optimal in every state of the Markov chain. And then the word Markov here means that this is something that's designed for memoryless strategies. So strategies that satisfy the Markov property that they only depend on the current state, not on the history. Okay, so this is quite similar to subgame perfect equilibrium. The idea is that we're going to have no profitable one-shot deviations for any player in any state of the Markov chain. And similar to how it was for MDPs, it's going to be enough to only check deviations in the first round only. This is because the Markov property gives us a kind of self-similarity that all of the optimality conditions in every stage end up being exactly the same. Defining or kind of saying what is the payoff of a one-shot deviation is a little bit fiddly. So I'm kind of resorting to writing this in words or saying it in words rather than trying to define this by formula, because at this point, things are so complicated that the formulas are not really very kind of transparent what they're trying to say. So I find it clearer to say in words. So suppose we have a stochastic game and we fixed a strategy profile, that is to say a function from states to actions for every player. Now, suppose we fix a start state, which we'll call Q0, and we want, so at that point, our particular player I gets some payoff from following their policy, their strategy, together with all the other players following their strategy. Stochastically, they get an expected payoff. Total discounted payoff. That's the thing that we defined in the previous video. Now we need to say what would be the payoff of a one-shot deviation. So one-shot deviation is going to, player I is going to play some other action besides what their strategy says to do. Every other player is going to still play their action that their strategy says to do. So that gives us a different probability distribution on the next state. Now, once we reach the next state, we're going to return to business as usual. So, so player I is only going to, it's a one-shot deviation, so they're only going to play a different action in the first round. Once we've reached the next state Q1, everything is going to return to being fully controlled by the strategy profile sigma. So that's very wordy, but that means that the payoff for player I of the one-shot deviation is going to be their expected payoff from the first round of that action, plus the discounted payoff from all future rounds of returning, not deviating, but returning to their strategy. And hopefully this has made you think about value functions. Okay, so this is quite complicated, but we can simplify it using value functions. So if we have a stochastic game and we fix a strategy profile for it, we can define a multi-agent version of the value function, which is a function that says for every state, what is the payoff vector for all players? And it's going to be defined in the way that we defined payoffs for players in the previous video, that the ith element of this vector is going to be this expectation of this infinite sum. So it's the sum of all of the ith players' payoffs. So given that all of the actions are given by what the strategy profile says to do. For example, let's look at the social dilemma example from the previous video. So that's this thing. So suppose we have two players here, and we have the strategy profile where both players have the same strategy, which is to do non-sustainable in the good state and sustainable in the bad state. So that's a strategy profile. That's with probability 1. So we can, similar to what we did with MDPs, we can kind of just plug the strategy profile into this thing, and we get a Markov chain with a payoff vector on every edge. So for example, in the good state, then with probability 1/2, we get payoff of 10/10, and we transition back to the good state, payoff probability 1/2, get 10/10 go to the bad state, and then similarly in the bad state we get no payoffs, and then we wait to, with probability 0.1, we transition back to the good state. Kind of by common sense, both players are going to have the same value function because they're doing exactly the same thing and they share the same state. So call this thing V, and then you can kind of eyeball this and work out what recurrence equations V would have to satisfy. So the value of the good state is going to be, we're going to get 10 plus a discounted copy of either a half-weighted copy of the value of the good state or a half-weighted copy of the value of the bad state, because of where we could transition. And then in the bad state, we're going to get 0 plus, and then a discounted copy of a 1 to 9 weighted value of the good state, value of the bad state. And again, we can solve this by pure algebra, which I have not done. Okay, so we can equivalently characterize Markov perfect equilibria using the value function, because when you deviate, when you do a one-shot deviation, it's just in the first round, and then after the first round, you return to your strategy, which means that the values are given by a discounted copy of the value function for that strategy. So, as is to say, the payoff to player I of deviating to some action in the first round is going to be this thing. So, the expected value of the utility now plus discounted value of the next state given current state and the action, and by this I mean every player that isn't player I is doing the action given by their strategy, and so sigma is a Markov perfect equilibrium exactly when no player has a profitable deviation for any start state. So notice that this is kind of similar to a Nash equilibrium. Nash equilibrium, this is like no player has a profitable deviation, except that the strategies are kind of affecting payoffs in an additional way. So if we have a Nash equilibrium for a normal form game, the mapping from strategies to payoffs is just kind of look it up in the payoff matrix. So this is kind of like Nash equilibrium, except that strategies are going to affect payoffs in an additional way, both via the individual stage payoffs and then also by kind of the value function, which is representing all of the future rounds. So it's kind of this, you can think of this as a kind of more complicated version of Nash equilibrium. Okay, now we also have a multi-agent version of value iteration. Specifically, if we're given a strategy profile, we can still estimate or learn its value function by the kind of multi-agent value iteration. What we can't do is learn the optimal value function easily anymore. So let's talk about this. So it's kind of the obvious thing. So the value function, or any value function, can be represented as a Q by N matrix. So say we get a real number for every state and every player. And if you think about it, the value for the ith player is only going to depend on the previous estimate for the same player. Players don't care about each other's values. So the value for some player improving the estimate of the value for some player only depends on the previous estimate for the same player, never for other players. We can go back to, where was it written? Oh yeah, here, right. Just to say the ith, so the ith player's value depends only on the ith player's payoffs. So what that means is that this method can be parallelized. So instead of having a q by n matrix, you just have n many q long vectors. The kind of upshot of this is that if we think of agents as being physically separate, then every agent can kind of take responsibility for computing their own value function independently, with the caveat that the policy in question, the strategy profile, does have to be communicated up front. So everybody has to have a copy of the strategy profile, but once that's been communicated, there's no more communication needed, and physically separate agents can estimate their own value function independently. This is basically the first time we're thinking of players in game theory as being kind of embodied in the world as in a physical location. And anyway, for convergence of this method to the kind of true value function of the strategy profile is still guaranteed for basically the same reasons. So we can use the contraction mapping theorem. Now this is for given a strategy profile. So previously we had two versions of value iteration, one for any old strategy profile and the more useful one for the optimal value function. So now we don't really have such a thing as the optimal value function because Markov perfect equilibria are not unique. And there is really no equivalent of value iteration for the optimal policy. Or to the extent that there is, it requires computing a Nash equilibrium once per iteration, which in small cases, for small games, you can do this, although then it can't be parallelized anymore, of course. But this gets very infeasible very quickly.